So Quirino, maybe you can share your screen.
Yes.
And so Quirino D'Amato will present the 2.1 GHz SHORES survey, exploiting the synergy between ALMA archive and deep radio observations. Quirino, the floor is yours.
Thank you. So today I'm going to talk about the importance of the far-infrared radio correlation to test several evolutionary galaxy models and how we used the novel 2.1 gigahertz observation of a sample of lensed galaxies in the GHz survey to push the study up to redshift 4, also using ALMA data to confirm the lensing measures of these candidates. And then I will talk about new observations at 2.1 gigahertz obtained with the Australian Telescope Compact Array that we added to the previous one in order to build a wide and deep radio survey featuring multi-wavelength coverage, including ALMA observations, that will allow us to investigate the nature of the faint radio sky population. So the far-infrared correlation is well established in the local universe. It's known since 1985 and is related to the correlation between the radio luminosity or flux and the flux or luminosity in many far-infrared bands. You can see here that this correlation stands in all the IRAS, WISE, and Herschel bands. This correlation indicates that the infrared emission and the radio emission have a common origin that is ascribed to star formation processes. So as for this correlation, the studies of this correlation at high redshift, this correlation is usually quantified as the ratio between the far-infrared and the radio luminosities, known as the Q parameter. And this recent study shows how this correlation stands also at high redshift, showing a quick redshift evolution up to redshift 2. However, if we want to investigate this correlation at higher redshift, of course, we need to detect fainter objects. In this case, the lensed galaxies come in help because they can, of course, benefit from the magnification. So we started from a sample of lensed galaxies candidate selected by Negrello et al. In 2017 in the H-Atlas field, in particular in the South Galactic Pole, that is field covered by the Herschel observations, and that also feature multi-wavelength, great multi-wavelength coverage from the UV to the millimeter band, and that allow us to fully characterize the properties of these objects. And so we targeted with 2.1 gigahertz observations with ATCA 30 fields around 30 candidates lensed galaxies. So these are the results. You can see here the sources in our sample. The dark blue one are confirmed lensed galaxies. And you can see that we can confirm the mild redshift evolution up to redshift 4. And as for the lensing nature of these objects, many of the confirmation have been made thanks to a high resolution observation, and in particular, thanks to ALMA. You can see here in HST images, for example, in which you can see the ALMA contours superimposed that clearly show the typical Einstein ring of the lensed galaxies. However, if you want to see the kind of treasures that these are all ALMA archive images. So if you want to see the kind of treasures that this archive hides, especially in terms of lensed galaxy, I invite you to listen to the Marika Giulietti talk today. If we put our result in the galaxy evolution context and compare it with other results, we can see that the Q parameters of the ratio between the luminosity in the infrared band and radio band is nearly as a function of the radio luminosity is nearly constant for dusty star-forming galaxies, so for objects in which both the radio and infrared luminosity are driven by star formation. However, for AGN-dominated objects in which the radio emission is dominated by the AGN, we see a decreasing trend as a function of the radio luminosity. And this can be put in the frame of a secular evolution scenario. You can see here the gray shade is the prediction of this model, in which we have an initial phase in which we have the star formation at the black hole accretion is a time coordinated process in which we have an initial phase in which the star formation occur in a dust shrouded environment, and then the AGN feedback remove the gas, quench the star formation, revealing the hidden quasar. So this means that in the faintest objects in a galaxy, in overall galaxy population, as the flux decreases, the objects start to be dominated by star-forming processes. So we have a radio flux regime that is around 100 microjansky, in which the overall galaxy population is a mix between star-forming objects and radio-quiet AGN. And study this kind of population is really important to test galaxy evolution model, because you can see here the prediction of the in situ scenario that I described before, in which there is a radio luminosity in which the star-forming galaxies start to take over the AGN population. In order to perform this kind of study, so we need to make basically radio counts or radio luminosity function of galaxies in which we can disentangle the contribution between the star formation and the AGN. So we need wide and deep radio survey featuring multi-wavelength coverage to perform the acid defeating of these objects. And in this case, the H-Atlas field that I showed before is a great candidate. So you can see here the UV plane of the previous observation in orange, and to which we we proposed and obtained new observations, adding more than 200 hours of observations, always at 2.1 gigahertz with ATCA. You can see here that these observations were partially carried on site. Is a picture that I took there in Narrabri, where you can see that I was in good company. And the aim is to fill the gap in the UV plane of the previous observations in order to improve the UV coverage and lower the sensitivity, and reaching sensitivity threshold, 5 sigma sensitivity threshold of about 100 microjansky that I showed before is the threshold at which the star-forming objects start to take over the AGN population accordingly to the model. So we expect to detect several thousands of objects in a 10 degree squared area. And all these fields in the H-Atlas field feature multi-wavelength coverage, as I showed you before, that will allow us to perform acid fitting of all these objects, deriving their photo photometric redshift, and disentangle the star-forming contribution to the AGN from the AGN contribution. You can see here a comparison of our survey with or other currently available. In addition, for one of this field, we added more than 20 hours of observation just on this field to push the limit to a noise of about 810 microjansky, and for this object, for this field, the data reduction is already done. You can see here that we can reach a reliability detection at 90% at a signal to noise ratio of 4.5. So this is the field, and with this threshold, we already detected more than 200 objects, and more than 20% of them have a flux limit that is below 100 microjanskis, so below the threshold that we expect to reach in the overall survey. And you can see here that the ratio between the total flux and the peak flux as a function the signal to noise ratio. So this ratio is a proxy of the resolved fraction of objects as a function of the signal to noise ratio, because of course the objects that have the total flux below the peak flux, this is just due to the error in the detection process, in the detection algorithm. So these are intrinsically undetected objects. So if we draw a line that encompasses of all these intrinsically unresolved objects, and we mirror it above the one line, the one-to-one line, you can see here that all the objects above this line are considered resolved. So we have also many resolved objects in this survey, meaning that we can also put the size of this object in relation with all the other properties of the galaxies. In addition, we also obtained a follow-up always with ATCA of the same field at 5.5 gigahertz, 9 gigahertz and 20 gigahertz observations frequency, and this will allow us to match the sources in our catalog with those that we will find in this other wavelengths, and this will allow us to fully characterize the radio spectrum. Thank you.
3 minutes.
The radio spectrum of high redshift galaxies. In addition, Mariam Behiri will talk about this during this meeting. So pay attention to her talk if you're interested in this. And in addition, I want to say that we also care about to observe polarized calibrators. We will also be able to perform polarization calibration for this survey. So we will also investigate the radio polarization fraction in this survey that has also consequences in the cosmological frame. Finally, this survey, as I showed before, feature also an important ALMA coverage, and to this one of about 100 arcminutes squared, and to this coverage, new observation at high resolution are going to be publicly released in these months. And this is important to also, you can see here just a few examples which have many objects. These are all archived images. I want to point out this. So some of them are lensed galaxies. So we are planning to use these observations to increase the statistics of the far infrared radio correlation and studies. And in addition, we are also developing a UV plane stacking code that will allow us to characterize the gas and dust content of different galaxy population. Martina Torcello will talk about this for the sources that will be not non-detected in the radio survey. So I leave you with my conclusions. I just want to point out that this survey, the data reduction of which is currently ongoing, is really promising due to its characteristic, deepness, wideness, and UV multi-wavelength coverage in order to study the radio sky population. Thank you. So if you have any question, I'm here.
Thank you, Quirino, for your really nice talk. Do we have questions? Yes, we have one from Abhijit. Does the accretion mode, high accretion quasar mode versus low efficiency radiation mode of the AGN have an effect on the far infrared or radio ratio?
Yes, so I think I have a slide. I have this slide that just by chance answer to this question. This is a study that I did last year, in which you can see here that I put the correlation between the radio survey and the radio emission and the X-ray emission for a sample of X-ray dominated objects. And you can see here that the efficiency for different objects that are spectroscopically classified as star-forming galaxies, local early type galaxies, and high redshift AGN. You can see here that for the early type galaxy and the high redshift AGN, we observe a correlation between the two emissions. Now, I do not enter in the details, but the slope of this correlation can be linked to the efficiency of the accretion process. And but in particular, you can see the star-forming galaxies. The star-forming galaxies do not show a significant correlation between the radioluminosity and the X-ray luminosity. This is due different contribution to the AGN object. So up to your question, of course, the efficiency is not direct of the AGN is not directly probed by far infrared emission, but it is important to have multi-wavelength coverage of these subjects to characterize also the accretion process of the subject and disentangle the different contributions also to the obscuration that affect significantly the high frequency observations and can lead to mistakenly identified many of radio objects as radio quiet while they are not, and so biasing this kind of studies.
Thank you. Do we have another question?
No, nothing from Slack at the moment.
Okay, so maybe if one question pops out, you can ask Quirino directly in Slack, and we can go to Antonio's talk.
Thank you.